Hi, my name is Gili Karni, and I will be presenting the work on fairness and stability in two-sided matchings. This is a joint work with Rothblum and Yona from the Weizmann Institute. Human decision makers are increasingly being replaced by algorithms. For example, setting bail in the American legal system, selecting ads to show on websites, and more. These algorithms usually maximize some utility function. However, because they involve high stakes for the participants, it is also important that they do not discriminate. Specifically, we focus on one-to-one allocation problem, where each individual receives a single outcome. We want to find an allocation that is both fair and useful. We use the setting of two-sided matching. As a running example, let us consider the allocation of doctors to hospitals for residency. Each hospital is matched to a single doctor. Our goal is to find a full matching between two sets of the same size, doctors and hospitals, in which each doctor or hospital has an ordinal preference over the other set. As an example, consider these preferences, where the violet doctor prefers the yellow hospital over the blue hospital and the blue hospital over the white hospital. Similarly, the yellow hospital prefers the violet doctor over the blue doctor and the blue doctor over the green doctor. The goal is to find a matching that is stable, which is defined by the absence of blocking pairs. A blocking pair consists of a doctor and a hospital that prefer to be matched with each other rather than with their matched partner. As an example, consider this matching. Since the violet doctor prefers the yellow hospital over the blue hospital, and the yellow hospital prefers the violet doctor over the blue doctor, this matching is not stable. This is because the violet doctor and the yellow hospital prefer to be matched instead of participating in this specific matching. This notion of stability was introduced in the seminal work of Gale-Shapley, who showed that a stable matching always exists and can be found efficiently. Our goal is to find a stable matching that is also fair to the doctors. Before formalizing what fairness even means in this context, one issue is that the preferences of the hospitals might not be fair to begin with. A discriminatory hospital preference may lead to an unfair matching. As an example, if some prestigious hospital prefers doctors from one ethnic group over doctors from another ethnic group without considering their merits, this may lead to an unfair matching. However, if the preferences of the hospitals are fair, will this guarantee a fair matching? We show that even if the preferences of the hospitals are fair, it is not clear what it guarantees. Our main question is, are fairness and stability compatible? Another problem is that under our requirement for fairness, which I will define soon, a deterministic matching does not always exist. Rather than a deterministic matching, we would like to find a probabilistic one. That is, a distribution over matchings. Our fairness and stability requirement are a priori, meaning over the distribution. To begin, we will consider a limited setting, where we assume that the preferences of the hospitals are in a restricted class of fair hospital preferences. I will explain this assumption in more detail shortly. Based on this assumption, we present two results. The first result is that, although we assume that the hospital preferences are fair, simply running the Gale-Shapley algorithm is not sufficient to guarantee that the final allocation is actually fair. However, in our second result, we present an algorithm that does ensure both fairness and stability under this assumption. It is based on the structure of the Gale-Shapley algorithm. Lastly, we show that if the assumption is even partially removed, no Gale-Shapley style algorithm is able to achieve both fairness and stability. We show this by defining a general algorithms class and showing that any algorithm in this class fails. In order to show our results, I will first define what is a fair matching, what is our stability requirement in a probabilistic setting, and what are fair hospital preferences? For the fairness requirement we use, we assume a given similarity metric, a distance function. This metric should be unbiased and should only consider the merit of the doctors. The distances between two doctors are between 0 and 1, and the metric is actually a pseudometric. That is, we allow two different doctors to have the distance of 0. Much of this work is focused on protometrics, metrics in which distances are either 0 or 1, meaning that every two doctors are either the same or completely different. According to this definition, the doctors are divided into clusters, where the distance between doctors in each cluster is 0, while the distance between doctors in different clusters is 1. The definition of individual fairness proposed by Dwork et al. Takes merit into account and says that similar doctors should have similar outcomes. However, what if they have different preferences? For instance, based on geographic location. A pair of equally capable doctors could prefer different hospitals and shouldn't be forced to have the same outcome just because of the fairness requirement. So, instead of individual fairness, we use preferences-informed individual fairness, or PIF, proposed by Kim et al., which is a relaxation of individual fairness and allows deviations from individual fairness as long as they are aligned with the doctor's preferences. I will present the fairness requirement over the allocation, PIF, under the assumption that the similarity metric is a protometric. That is, the distances are either 0 or 1. Restricting our attention to this simple setting simplifies the definitions, but the paper also studies the definitions in more general settings. Between clusters, meaning doctors that are in distance 1 from each other, we have no guarantee, that is, no fairness requirement to enforce. In each cluster, doctors that are in distance 0 from each other, we require envy-freeness, which implies that each doctor prefers its own allocation over the allocation of any other doctor in its cluster, according to this doctor's preferences. The outcomes are compared using stochastic domination. According to doctor's I preferences, allocation P stochastically dominates allocation Q if for every K, the probability of being allocated to the top K outcome, according to Dr. I's preferences in P, is greater or equal to that in Q. For example, the probability to be assigned with the Dr. I's first choice in P is greater or equal than in Q. Similarly, the probability of being assigned to Dr. I's first or second choices in P is greater or equal than in Q, and so on. Hence, to have a fair allocation, each doctor's allocation should stochastically dominate the allocation of its peers in the cluster. This concludes the definition of fair matching. We are now prepared to define fair preferences. For a protometric, a natural definition for fair preferences would be to require indifference between doctors in the same cluster, meaning that the hospital would not be allowed to favor one doctor over the other if their distance is 0. However, we do allow hospitals to have order preferences over the clusters. That is, doctors who are in distance 1 from one another. Another way to view the definition is a probabilistic representation of the preferences. We can represent the preferences of each hospital using a distribution over ordered preferences. That is, a distribution over the order of a complete list of the doctors. The order of the clusters is chosen as before, and the order of the doctor in each cluster is randomly chosen from the uniform distribution, independently of the order of the doctors in other clusters. This concludes the definition of fair hospital preferences. Next, I will define stability in this probabilistic setting. With the deterministic definition of fair hospital preferences in mind, we are able to naturally generalize the definition of stability. According to the classical deterministic definition, a matching is unstable if there is a blocking pair. That is, an unmatched pair that prefers each other to their match. In a probabilistic case, we make the same requirement over the matchings in the support of the allocation. Moreover, we require strict preference, which means that a hospital cannot be in a blocking pair with a doctor from the same cluster as his matched partner, since it is not permitted to have strict preferences between doctors in the same cluster. To conclude, we say an allocation is unstable if there exists a matching in the support of the allocation that contains a pair of a doctor and the hospital who prefer each other over their partner in the matching, and the doctor in the pair belongs to a different cluster than the partner of the hospital. We discussed the definition of stability for unfair hospital preferences in the paper. To conclude, we use a metric-based fairness definition, focus on protometrics, which are metrics where the distances between doctors are either 0 or 1. We say an allocation is fair if it satisfies envy freeness within each cluster. That is, every doctor prefers their own allocation over the allocation of any other doctor in the cluster. We say the preferences of a hospital are fair if it has strict preference over the clusters and is indifferent between doctors in the same cluster. In addition, we had a probabilistic representation of the preferences, where the order of the doctors in the same cluster was sampled uniformly at random. Finally, we define stability as the absence of blocking pairs in any matching in the support of the allocation, with hospitals only allowed to be in a blocking pair with doctors from different clusters than their partner in the matching. Next, I will present the first result, that under the assumption of a protometric and fair hospital preferences, running the Gale-Shapley algorithm fails. Our approach builds upon Gale and Shapley's two-sided stable matching algorithm, which I will present now. In this problem, we match two sets of the same size, where each individual in each set has an ordinal preference over the individuals in the other set. In our example of doctors and hospitals, each doctor has preferences over the hospital and vice versa. In the algorithm, each set plays a distinct role. One set is the proposing set. Without loss of generality, let's assume that these are the doctors, and the other set is the accepting set. We'll assume that these are the hospitals. The algorithm works as follows. While the matching is not full, an unmatched individual is chosen arbitrarily from the proposing set. In this example, an unmatched doctor. Currently, no doctors are matched, and so the violet doctor is chosen arbitrarily. This violet doctor proposes to their most preferred hospital, the yellow hospital. Since the yellow hospital is not matched, it accepts. Now, the only unmatched doctor is the green one, so they have to propose. The green doctor proposes to their most preferred hospital, the yellow hospital. The yellow hospital is already matched. Thus, it has to decide whether to stay matched to the violet doctor and reject the green doctor, or reject the violet doctor and become matched to the green doctor. As the yellow hospital prefers the violet doctor over the green doctor, it will reject the green doctor. Once the yellow hospital rejected the green doctor, this doctor removed the yellow hospital from their list of preference and would never propose to it again. Since the green doctor remains the only unmatched doctor, they are chosen again. Now, they will propose to the green hospital, which is unmatched and therefore accepts. Since there is no unmatched doctor, the algorithm is terminated with this matching that is stable. Next, I will demonstrate how we use the Gale-Shapley algorithm in our probabilistic setting. A natural first step was to require fair hospital preferences and then apply the Gale-Shapley algorithm to these preferences. I said earlier that the hospital preferences are fair if the hospitals have strict ordinal preferences over the clusters and are indifferent to doctors in the same cluster. But how can we run the Gale-Shapley algorithm over such preferences? We can use the probabilistic representation and sample the preferences. The preferences are represented as a distribution over ordinal preferences with the same order of the clusters, where the order of the doctors in each cluster is chosen uniformly at random. We then find the probabilistic allocation by sampling this distribution of each hospital preferences and running the Gale-Shapley algorithm over the sampled preferences. The probabilistic allocation is the resulting random variable. Hopefully, the fairness of the preferences will imply a fair allocation, but actually, this approach fails. This result joins existing work that shows failure of composition in fairness. That is, all the participants acted fairly, and the mechanism seems unbiased in that it doesn't explicitly favor some of the doctors over the others. Yet the outcome is still unfair. Here, I will show a counterexample for the case where the doctors are the proposing set. In the paper, we also provide an example for the case where the hospitals are the proposing set. In this example, there are 3 doctors and 3 hospitals. The blue and violet doctors are in the same cluster, and the green doctor is in a different cluster. These are the preferences. As you can see, they are fair, since the hospitals are indifferent between the blue and violet doctors, such that their order is chosen uniformly. However, if we sample these preferences and run the Gale-Shapley algorithm, where the doctors propose to the hospitals, we get the following allocation, which is unfair with respect to the blue doctor. To have a fair solution, we require envy-freeness within each cluster in terms of stochastic domination. The blue doctor's first choice is the yellow hospital, and they are never matched. On the other hand, the violet doctor is matched with the yellow hospital with probability half. Therefore, the violet doctor has a higher probability of getting the blue doctor's first choice than the blue doctor, which means that the blue doctor's outcome does not stochastically dominate the violet doctor's outcome, and the matching is not fair. We get this surprising result, although we required symmetry in the hospital's preferences. The preferences of the blue and violet doctors are not symmetrical, since the blue doctor prefers the green hospital over the white hospital, and the violet doctor prefers the white hospital over the green hospital. Hence, although the yellow hospital accepted or rejected the blue and violet doctor's proposal with the same probability, the different preferences cause a difference in later rounds of the execution, causing the yellow hospital to reject the blue doctor in one case, but not reject the violet doctor in the other case. This raises the question of whether this failure is specific for the Gale-Shapley algorithm or inherent to the problem. I just showed that the naive approach of sampling fair hospitals' preferences and running the Gale-Shapley algorithm fails. Next, I will present the second result, an algorithm that guarantees both fairness and stability. I will show an algorithm that approximately solves this problem under the assumption of a protometric and fair hospital preferences. The algorithm is called fair propose and reject. Unlike the previous approach of sampling and running the Gale-Shapley algorithm, hoping that the fair hospital preferences will ensure a fair outcome, we force the hospitals to make the decision simultaneously for all the doctors in the cluster. We do that by allowing the participants to propose and accept probability mass. At the end of the run, we have an n over n matrix, which represents the probability of each doctor to be matched to each hospital. In order to extract the distribution over matchings, we use the Birkhoff-von-Neumann algorithm. Our algorithm has 2 variants, one with the doctors proposing and one with the hospitals proposing, similar to the Gale-Shapley algorithm. Here, I will describe the version in which the doctors propose. In the beginning of the execution, every doctor has free probability mass initialized to 1. On the right side, you can see the preferences of all the participants. The algorithm proceeds in rounds. In each round, each doctor proposes all the free probability mass they have to their favorite hospital, as long as this hospital hasn't rejected them yet. This is similar to the proposals part in the Gale-Shapley algorithm. However, in this algorithm, all the doctors propose simultaneously. In the first round, the blue and violet doctors propose to the yellow hospital, while the green doctor proposes to the white hospital. These hospitals has now probability mass proposed to them, and they have to choose which of it to accept. The mass proposed by each doctor represents the probability to be matched to that doctor in the final allocation. This is similar to the Gale-Shapley algorithm, where individuals can choose to accept a new match or stay with their existing one. In this case, the yellow hospital has only probability mass 1 proposed to it, so it accepts all of it, because it prefers being matched to the green doctor over not being matched at all. The yellow hospital has probability mass 2 proposed to it, and it must accept no more than 1, in a way that will not cause unfairness. This mass is proposed from 2 doctors that belong to the same cluster. Therefore, it is clear what to do here. Accept half from each of them. They will keep going with the remaining mass to the next hospitals in their preference lists. That is basically our algorithm. The question is, in general, how a hospital decides when it is given a lot of different units of mass from different doctors in different clusters. We use an algorithm we call the rising tide algorithm to describe which probability mass to accept. Our algorithm is called the rising tide algorithm because it reminds us of the law of communicating vessels. Each doctor is represented by a vessel with the same width, and the capacity of the vessel is determined by the probability mass this doctor proposed to this hospital. In each cluster, all the vessels are connected. In the beginning, all the hospital's mass is unallocated. We can think of the unallocated mass as water. The hospital goes over all the clusters, starting with the most preferred cluster and ending with the least preferred cluster, and tries to pour water into the vessels of the doctors in the cluster. If all the vessels are full, it moves to the next cluster with the remaining water, until it has no more water to pour, or all the vessels are full. The water poured to each vessel represents the accepted mass from that doctor. That way, it will first accept probability mass from the clusters it prefers more. Also, in each cluster, all the doctors will have the same amount of mass accepted, unless they proposed less than others. In that case, they reached their capacity, meaning the entire mass they proposed was accepted. Let's go back to the algorithm. We had 2 clusters of doctors, one with the blue and violet doctors, and one with the green doctor. At the beginning of the round, each of them proposed to their favorite hospital their entire free mass, which was 1. Now the hospitals have to decide what mass to accept. The mass they accept from each doctor represents the probability to be matched to this doctor in the final allocation. The white hospital was proposed with mass of 1, so there is no problem, it will accept all of it. The yellow hospital, however, was proposed with total mass of 2, which is larger than 1. Thus, it must reject at least 1 in order to accept a mass that will represent a distribution. Since the yellow hospital was proposed with mass from a single cluster, it will run the rising tide algorithm and accept half from each doctor while rejecting half from each doctor. As a result, the rejected mass becomes free. Since the blue and violet doctor were rejected by the hospital, they will never propose to this hospital again. Next, the blue and violet doctors propose to the next hospitals in their preference list, the blue and white hospitals. The green doctor does not propose since they have no free mass. Because the green hospital was proposed with less than probability mass 1, it will accept all of it. The white hospital has the mass proposed to it in the previous round from the green doctor, and the mass proposed to it in this round from the violet doctor, and it has to decide which mass to accept and which mass to reject using the rising tide algorithm. As the first cluster in its preference list is the cluster of the blue and violet doctors, it will accept probability mass half from the violet doctor. Since the blue doctor did not propose any mass, it is okay to accept an unequal amount of mass. Since there is only half unallocated mass left, it will accept only half probability mass from the green doctor. Therefore, the white hospital rejects half of the probability mass from the green doctor. As a result, this mass becomes free, and the green doctor will never propose to the white hospital again. In the next round, the green doctor proposes to the yellow hospital, since it is the first in their list, excluding the white hospital. The blue and violet doctors does not propose since they do not have free mass. The yellow hospital must now decide whether to accept the mass it already accepted or the new proposed mass using the rising tide algorithm. The first cluster in its preference list contains the green doctor, so the yellow hospital accepts all the probability mass proposed by them, which is half. The next cluster contains the blue and violet doctors, who each proposed half probability mass. With only half unallocated probability mass left, the yellow hospital will accept a quarter from each of them and reject a quarter from each of them. The rejected mass becomes free again. However, since they were already rejected by the yellow hospital, their preference lists remain unchanged. They will propose to the next hospital in their list, which is the green hospital for the blue doctor and the white hospital for the violet doctor. But notice, these are exactly the same proposals as 2 rounds ago, but with half the free mass. Therefore, the algorithm will never terminate. However, it will converge since the amount of free mass keeps getting smaller. We stop when the free mass drops below some threshold, and this is what makes the output of the algorithm approximately fair and stable. Next, I will present a proof sketch for the correctness of the algorithm. In order to prove stability, we must prove that in any matching in the support of the allocation, there are no blocking pairs. Doctors can only be part of a blocking pair with hospitals that rejected them. Let's say there is such a doctor in a blocking pair. Then the hospital in the blocking pair prefers this doctor over some doctor in the support of its allocation. According to the rising tide algorithm, we assumed that the hospital would fill the allocation by the order of its preferences. As well, the hospital can always choose the allocation from the previous round. Thus, the allocation can only improve. This implies that the hospital will always weakly prefer any doctor in its allocation to the rejected doctor, so no blocking pairs are possible. In order to prove fairness, we need to show that the allocation is envy-free within each cluster. That is, that each doctor prefers its own allocation to that of every other doctor within the cluster. Let's fix 2 doctors, D1 and D2, from the same cluster. To have envy-freeness in terms of stochastic domination, we have to make sure that for every K, D1 is assigned with its top K hospitals with at least the same probability as D2. In the rising tide algorithm, we said that if D1 and D2 propose to the same hospital H in some round, H will accept more mass from D2 than from D1 only if D2 proposed exactly the amount that was accepted by H. We allow that because we assume that this means that the rest of D1's mass is assigned to hospitals that D1 prefers over H. And then D1's allocation would stochastically dominate D2's allocation. However, what if it is not the case? What if D1 got rejected by H in an earlier round and it is assigned with hospitals it prefers less than H, which means that D1 envies D2? We show that this can never happen. If in some round D1 got rejected by H, then in any later round, no doctor from D1's cluster would be assigned with higher probability mass from H. Since each probability mass can be rejected only once, the algorithm converges but not necessarily stops. We stop when the total amount of free mass drops below some threshold. In this work, we showed that under the assumption of a protometric and fair hospital preferences, there is always a fair and stable solution, and it can be found using our algorithm. But what if we removed one of the assumptions? We show that in that case, no algorithm in the style of the Gale-Shapley algorithm guarantees both fairness and stability. We show this by defining a general algorithm class that contains algorithms of this type. Here, I present the subclass where the doctors are proposing. But in the paper, we also show the corresponding class where the hospitals are proposing. All the algorithms in the class proceed in rounds. In each round, the doctors propose their free probability mass to the hospitals. We assumed that the doctors must propose by the order of their preferences. After the proposals, the hospitals can choose which mass to accept and which mass to reject. We assumed that after the mass was rejected, it cannot be proposed again to the same hospital. The algorithm stops if there is no free mass or if the free mass is very small, as we did in our propose and reject algorithm. These algorithms are local in the sense that each participant has to be aware only to its own preference and act upon it. There is no central decision maker. We showed that for this class of local algorithms, there is no algorithm that guarantees both fairness and stability. The full proof of this result is in the paper. To conclude, we showed that under the assumption of fair hospital preferences and the protometric, there is always a fair and stable solution. Also, we showed an algorithm that finds it. In all the other cases, we showed barriers in finding such an algorithm, inclining that if such an algorithm exists, it will require a different approach. We are still left with some open questions, such as, are fairness and stability compatible in the general case? Is there an efficient algorithm to find such a matching or say whether it exists or not? There are also questions about the properties of the algorithm we found, whether it is incentive compatible or optimal to one of the sets. We leave these questions open for future research. That's it. Thank you for listening.